Good morning, everyone. Welcome to our lecture. I see some folks there still joining. Welcome, welcome. We're gonna start in a minute. Hope everyone had a wonderful weekend and you ready for another week. This is we are in June. Next month is our last month, basically, and at this point, I want to bring to your attention that please continue uh, reading, starting the course, starting the material, going over the review, using the review session. I will share before we get started with our lecture this morning, share with you um, the stats or statistics for the midterm exam number one and what we may need to do for the next midterm exam. I'm going to share with you, and please email me any concern you may have. But in the meantime, please make use of the SI support session. There is a schedule for that. In the past, students tend to stop attending the session thinking that since they did well in the first exam, probably they will do well in the subsequent exams and even the quizzes. Remember, as we go along, new concept, new techniques will come along. It's not like, we start with the basic stuff and then new material will be introduced during the course of the semester. So let me share my screen here and I'll give you, I'll show you the stars. We will see how we did in the exam before we get started. I want to share with you. You can see where you are. This is, all right, this is the statistics. And average for the midterm exam number one was 89, which is good. It's impressive. It's not that bad. The highest was 98, and the lowest was 62 with a standard deviation of 7.79. Average time taken to complete the exam was about 1 hour. So the time allocation, you had enough time to complete. Remember, you had the entire lecture session to complete. What you see here is the average. If you look at the statistics, most folks they were in 90s. If you are somewhere here, please attend the SI session. Please attend the SI session. Email me if you need some extra time. I'll try to help you. So this is where we are. Relatively, I can say you did well. Please do continue with the same strategy for starting the material. So having said that, tonight, quiz number three, is due tonight, even though it was in the first exam, term exam number one. I wanted you to be responsible that don't say, why is he making the chapter 3 quiz due after taking the exam? It's your responsibility to stay on top of the game and complete. I'm just giving you ample time to do that. So having said that, let me just pull the PowerPoint slide where we stopped last time. We went as far as metathesis reaction, double replacement reaction, and how to predict, all right? How to predict the products for double replacement reaction. We have, all right, we have uh, 10 solubility rules you need to remember. But as I said, I'll allow you to use in the exam and in the quiz. I'll recommend that you print out the solubility chart you see here. This is the solubility table, which when you exchange the anions, polyatomic ion or monatomic ions, when they switch the ions, when the cation switch the ions, use this table as a guideline to predict the precipitate, the solid, okay? You need to indicate what is solid, precipitation falling down. It may not be, all right, you may not really have exact or all the ions, but you can use, all right, you can use the group number to predict how a particular ion will form a compound with a particular anion. For example, it's given here, group 1, somebody might say, I don't see sodium or I don't see potassium, you gotta use that. If I see barium, I can predict that magnesium, which is group 2, will react the same way, except some cases you may not have it here. But generally, most of the double replacement reaction you will encounter will be summarized by this table, all right, yes, somebody had a question about chapter 4. Yes, Tony, we started chapter 4, and I just mentioned at the beginning of the semester, like next month is the last, July 30th is the last day of the semester. Thursday, all right, which is the 29th, will be the last class meeting, which we will take the final, so it's rolling. Summer semesters are always rolling very fast, so stay on top of the game. Otherwise, you may, if you miss a couple of sessions for some reason, you may need to use the lecture recording, which I always post. And for last week, I do have already in the lecture recording module. So here is where we stopped in number 4, predicting the product in a precipitation reaction. What I have here is the whiteboard, and I want to use an example to show you how you can predict using the table. Suppose we have lead, all right, let's say lead 2 nitrate, lead 2 nitrate plus, and this is aqueous. Let's have the physical state, potassium iodide, and this is aqueous. All right, that is aqueous. What this means is what it is, or what are our products on, the right side of the equation. What I have there is potassium iodide, aqueous. This will call for, recalling what we learned in chapter 2, writing the correct formulas for compounds, all right, using the crossover rule, and then indicating the physical state. And in chapter 4, where we are, is predicting the correct formula. So when we write that, so what we'll do is assume that this is the reaction vessel, all right? Assume this is the reaction vessel right there. You need to write the ions in each reagent. Look at what I'm doing here, and I know from the polyatomic ion, I should know the formula for nitrate. Lead 2, the other positive 2, there is lead 1, there is lead 2. Please, Kerry, just get in touch with me. Finally, still far away. Please refer to the syllabus on the exemption. No exemption. Potassium iodide. These are the ions from the second reagent. I assume that here I have the addition. For metathesis reaction, it is double replacement reaction. So this means this will combine with that. This will combine with that. Look at my arrows, and then you write the correct equation. So if I do have here lead 2 nitrate, this is the lead 2 nitrate, with the 2 subscript aqueous plus Ki, this is aqueous. Now, my product will be, based on what I do have here, lead 2 iodide is P, not like that, it is I2 using the crossover rule, plus potassium nitrate. The question is, how will I know which one is aqueous? Sorry for writing the aqueous. I don't even know for the physical state. This is what I was saying, that the solubility chart we do have here will help you in predicting which one is solid, which one is aqueous. If I look at the nitrate, anything with a nitrate is aqueous, maybe D for decomposition. It will not, as soon as it's formed, it decompose. So you cannot have both solid. One has to be a precipitate. And if I look at the lead 2 and then iodide, this is iodide ion, this is lead 2 ion, where they intersect right here. All right, if I use the annotation to show you what is going on, right here is solid. So I know for sure the lead 2 iodide is solid. So what you need to do is write the physical state of lead 2 iodide in our equation. So this is solid right here. Let me use screen. This is solid. And of course, this is aqueous. You can use also the solubility chart. No one will tell you balance the equation. You are expected to always understand that from the law of mass conservation, you need to balance the equation, which means using trial and error, get the coefficient. We need that 2 in front of potassium nitrate and potassium iodide. The equation is balanced the way it is, and with this we have predicted the product of our metathesis reaction. So in the next quiz, make use of the solubility chart. I'll give you also in the exam to use that. Familiarize yourself on how to use the solubility chart. This concept here, all right, will take us to the next step, which is writing the molecular equation, the net ionic equation, complete ionic equation. For those who are taking the lab right now, probably you have covered that. If not, it is coming down the line, all right? So that is just a summary of how to write the correct equation predicting the precipitate in metathesis. Metathesis is basically a double replacement reaction. Metathesis is a double replacement reaction where cations do what? They switch the anion, You should be able to write the correct formulas for ions when we say sulfide, sulfate, nitrite, nitrate, and so forth, phosphate, phosphide, and so forth. You should be able to use in writing the correct formulas. This is what I wanted to bring to your attention, the 3 equations. This is just a summary. What you see on the PowerPoint slide is what I went through. How did I come up with the correct formulas. Chapter 2, crossover rule for what? For ionic equation. You may be presented also with the molecular compound. How do you write the formula for oxygen gas, nitrogen gas diatomic? It will impact when you balance the equation. And of course, using my diagram here, I was able to write the correct formulas by switching the ions, So this is what I want to bring to your attention about the 3 types of equation you should be familiar with, all right? To this point, and in Introduction to Chemistry, you are introduced to just balanced equation, and we call this molecular equation. Molecular equation is just a balanced regular equation indicating how many we have on either side, and then we have what we call the complete ionic equation. I want to here the second type right here, the complete sometimes this is called total ionic equation, total ionic equation. The second one here, the second type of equation we have here. I need to show you that complete ionic equation. Complete ionic. How do you generate this? This is built or derived from the molecular equation. There is no way you can start off from equation 2. You have to have the correct molecular equation to derive the complete ionic equation. And to do this, you split. This is how I will derive the complete ionic or total ionic equation. You split the aqueous. You know what aqueous? The aqueous phase in molecular equation. So if I have written down Palazzo equation for molecular equation, you will look at what? Aqueous, and then you split. I'm gonna show you how you split that. Leave alone, maybe I should say do not split. If there is solid, leave it alone. If there is liquid, leave it alone. If there is gas, leave it alone. You do not split the solid state, the liquid state, the gaseous state in molecular equation. I'm using what we had before to show you what I mean by that. Suppose in the molecular equation we do have this PP NO3 AQ. I do have here to write the correct formula. 2 aqueous. This is aqueous plus Ki. Remember there was a 2 there to balance the equation. This is aqueous going to PP I to this was solid plus 2K NO3, and this was aqueous. This is the balanced molecular equation. It is number 1 here. Now, number 2, you have to see where the ions are. You cannot split, for example, the first one here, oxygen and nitrogen. You have to split the cations. In other words, this is where I'm gonna split. I will separate layer 2 ion with the nitrate. I will split, should be well conversant with or well-rounded with the ions. No, not the solid. I meant to say we split we split this right here, the aqueous, not a solid. And then I go split this one. You have to see where the cation and anion. Remember the note I have below equation 2 there, you only split the what? Aqueous phase in molecular equation, leave alone solid. So we're not gonna mess with lead to ion. Now, when you split, the subscript changes to coefficient. This is what I mean by the coefficient. Look, for example, here at the first reagent, this is what you will need to come up with. Now, lead will not just be lead like that. It will not be like that. It will be in form of ion like that, and then you write aqueous. From the first reagent, the subscript changes to coefficient, NO3, that we have 2 nitrates, and then it is aqueous. Don't say, all right, I've split that, and then I have that, and then you have to, and then you, no. This is not the correct way of splitting or retaining. The subscript changes to what? To coefficient. So I do have 2 ions from the first reagent. The second reagent we have, all right, plus now we have 2 potassium ions, aqueous, plus 2 iodide ions. We do not mess with lead to iodide. Lead to iodide just stay the way it is. Just stay the way it is. Don't split solids. On the other side, I have plus 2 potassium ions and 2 nitrate ions, and these are aqueous. Suppose somebody, and I know I see quite a common mistake students do make is forgetting. If you forget to indicate the correct physical state from the molecular, from the first one here, it will be very difficult for you to know which one to leave alone, which one should I split, which one should I leave it alone. If you don't indicate, chances are you will make a mistake. You'll not end up with the right what? The right complete ionic equation. So what you see here is equation 2, where you only split the aqueous. Remember, the subscript changes to coefficient, leave solids alone, and that is what you end up with in complete ionic equation. Complete ionic equation.
I have a question.
Yes.
So when you split the aqueous molecules from both sides of the equation, you put all of them as the reactants and just keep the solid as the product?
No, if you look at, because of my whiteboard, I couldn't write, there's an arrow here. You see the arrow here?
Yeah.
So everything will be, whatever you have on the reagent will be on the reactant. Whatever you have on the product will be on the product.
Oh, okay. So I thought on the last slide, did you have some of the...
Let me just go back here. Is this what you're referring to?
Yeah, on the very bottom is...
I see I do have the reagent. This is the reagent, and this is one of the reagents. Sorry about that. What is the question here?
So the potassium nitrate on the very right.
Yes.
Like on the next slide, it's on the reactant side.
Oh, so maybe I put it. It is on the. It's not on the reactant side. This one, if you look at these two right here, these 2 ions here, they are coming from potassium iodide. These 2 are coming from the nitrate. So it is not potassium nitrate.
So all the aqueous creates a solid product, is that what you're saying?
The solid product is coming from when lead to ion combined with iodide ion on the reactant side, it gives us the solid on the product side. Look at this arrow here. This is the product, and these are the ions from.
Oh,
yes.
Okay. I didn't realize that was like also on the product side. Okay.
Yeah, like my whiteboard is like, I couldn't write on the other side.
Okay. Okay. Thank
Make
you.
sense?
Yeah.
Okay, all right. I think somebody had a question or wanted to chime in. Somebody had a question. All right. If no question, this is now in the exam or quiz, I may give you a balanced what? A balanced molecular equation, which is the first one here, and ask you which one of the following is a complete ionic equation. And then you pick the multiple choice. Or what is the what? The complete ionic equation for this. And it could be a chemical, an equation presented in chemical formulas. You may be given a water chemical reaction and you are supposed to write the chemical formulas and balance. So in most cases, it will be balanced. Now, the third one here, all right, the third type of equation is the net ionic equation. In the same sequence, you need to know the first one, that is molecular equation, in order to write the complete ionic equation. So net ionic equation also is built on the complete ionic equation. You need to nail down this second one in order to derive net ionic equation. For those who work like maybe two jobs or one job, they show you your paycheck shows cross, and then there is the net. You know what is meant by net? When they take away maybe social, maybe insurance or whatever, anything they deduct. Net is when you remove something. So when we say net ionic equation here, 3, net ionic equation, and from the word ion, so it's got to be ion, you derive this by remove or cancel. You may use your own terms so long as you know what you're doing. Remove what we call theta what ions in complete ionic equation. There is a new term here I'm using for the first time, spectator ions. When we call what the, let's say for example, football. And, we are spectators, we don't play. The players are in the field while everybody is just looking. They don't play, they don't participate. So in other words, spectator ions are those ions which do not form the solid, or in other words, spectator ions are ions which look exactly the same on either side of the reaction arrow. So if the arrow is here, if I look on either side, that is the product and the reagent, they look exactly the same. I need to cancel out. I need to remove those ions. So let's use that example here and identify the spectator ions. They should look exactly the same. I'm going to circle. If you look at this is a spectator ion. It looks exactly the same thing as this on either side. If this is our reference, this is where we are placing our comparison on either side of the reaction arrow. So I'm gonna cancel this like this because they look the same. The other one is, all right, the other one is this. Look at this. It is aqueous. This one is aqueous. So I'm just gonna cancel as well. I'm just gonna cancel this as well. They look exactly the same. If I look at lead ion, this is aqueous. It's not the same. It is in form of solid here. It is a precipitate. Doesn't look the same. It's in a different form. Iodide, two iodide ions here, they are not the same. So what I will be left with is this equation, and this is equation 3. And you need to write down the physical state, all right? And then say aqueous, and you indicate how many you have for each ions aqueous, and what we have here is lead two, and then solid right here. What I do have here is net ionic equation. I use the analogy of the paycheck that they deduct, and then you are left with something at the end. So we have removed what we call spectator ion, and the last equation is net ionic equation, net ionic equation. So if you derive the complete ionic equation and see which one is solid, which one is the precipitate incomplete ionic equation, and then you know what ions actually plays the formation of, or how to derive the net ionic equation. Net ionic equation. So, and having gone through equation 2 and equation 3, questions could be tailored along this line, that which one of the following is the net ionic equation, or what are the spectator ions for this reaction. All right, so if you don't know, if you are asked what are spectator ions, you should be able to write the complete ionic equation and write the net ionic equation and see which one will cancel out. That is what I need you to practice. I think there are a couple of problems in end of the chapter. Any question on the 3 types of equation? So yeah, that is the molecular equation, the net ionic equation. You can write that is the same thing. Remember, you need to balance. This is what we are used, just balancing the equation. But complete ionic equation is you split the what? Split the ions, and the coefficient, I mean the subscript changes to coefficient. We didn't split the solid, but we split the aqueous in complete ionic equation. And of course, net ionic equation, we remove spectator ions.
So I just want to make sure, because on the complete ionic equation slide, so it says, you know, strong acids, strong bases and everything like that. But then you were kind of just saying to split the aqueous solutions.
Yes, yes, if you going back to this, right? Strong acid, strong, you're talking about strong acid. Strong acid?
Yes.
Yeah, strong acid, remember what we define, and I think this is up in the upcoming section, we will look at the acid and bases. And strong acid completely ionized, which is ionized is splitting into, you know, ion and decation and anion. Basically, strong acid ionizes, and the splitting, even without using the word, all right, even without using the word split, or even without using the word strong electrolyte, basically, which means it will ionize, you end up with a complete ionic equation. It's the same thing, strong electrolytes or ionic equation. Still, the approach is the same in terms of splitting. The thing is now is identifying and knowing which one is a strong electrolyte, which one is a weak electrolyte, and how it will play out. For weak electrolyte, I don't really see quite a lot of question on weak electrolyte, because that is a gray area. Because if you are presented with a weak electrolyte and you are expected to write the net ionic equation, still you will see the original molecular compound, because not all of them will split. So
I see.
Most questions will be either strong electrolyte, which will 100% dissociate split. But when you're dealing with weak electrolytes, it's kind of like a gray area, and I don't, once we know the concept, I don't want to test you or grill you that much to that extent, because you try to cancel out, still it's gonna remain at the end. You understand?
Yes. Okay. So just, you know the rule, but you know, we're not really going to be tested that much on them.
Yes, exactly.
Awesome. Thank you.
Yes, that is what it is. Any other question? So that is complete ionic equation. How to go about with that? You'll be asked spectator ions. I've explained what spectator ions. You should know what they are. You may be asked what are spectator ions are. Identify the spectator ions. And the last equation you see here is the net. All right, this is the net ionic equation. I hope multiple choices will not be so tricky. Sometimes I see students saying that, oh, that was a trick question, in the sense that maybe this positive 2 will be missing in one of the multiple choice, and somebody will pick and say it look exactly the same as what the professor was going through. You have to be careful, read every detail. They say the devil is in the detail. Pay attention to ionic charges so that those doesn't cost you points. So I don't want to spend more time on net ionic equation. You can do that. This is a typical question. Look at the PowerPoint slide here. Let me just, last time somebody brought to my attention that, can you make the slides larger? Let me minimize my whiteboard a little bit and increase this for those who want the large PowerPoint slide. So this is the question. Which ions, if any, are spectator ions in this reaction? You don't need to derive. If I look at this, this is a solid, which means the nitrate and the sodium ion are spectator. Chloride ion is forming solid and cannot be cancelled out. It will remain in the net ionic equation. Silver, again, cannot be cancelled. It will remain in the net ionic equation, which means using elimination method, A is wrong. Yes, this is correct, but the chloride is messing up B. So this is the correct one. No spectator ions involved. It revolve around writing the correct net ionic equation. It's
So
pretty
the
easy.
answer was no spectator ions are involved.
Yeah, spectator ions are not involved in formation of the solid or precipitate, basically.
Why is it not C?
Yes, that's what I say is C.
Oh, it is C.
Yes.
Oh, okay.
Yeah, it's C. Because they don't participate in the formation of the precipitate. Now, section 4.3 is on, is still on double replacement reaction, metathesis reaction, but now focusing on acid and bases, all right? Acid and bases, there are three definitions of an acid. Yes, three definitions of an acid. And according to, let's just put here, there is Arrhenius, and then the Bronsted Lowry, that is Lowry, two Sandist, Divine, Blore, this Bronsted, this is R. Definition of an acid. I'm defining this term right here. According to Arrhenius, is this is any substance that produce hydrogen ion or proton, because we remove an electron, when dissolved in water, in H2O. So that means it must have hydrogen in the chemical formula. Anything with that means it's dissolved. So it's dissolved, and it ionized. Of course, we cannot get that. But Bronsted loaded definition is basically simply proton donor. They define that proton donor. And as paces here, or a pace, let me just go right there, according to Arrhenius and Bronsted, Lowry, Liowry. This is, or he divine, Arrhenius divine base as any substance that produce OH. This is called hydroxide ion. Dissolved what? Dissolved in H2O. Sodium hydroxide, you see there's NaOH. There is also example here is KOH, potassium hydroxide. There is OH in the chemical formula. Now, according to Bronsted, this is where now the difference comes in between the two definitions. In the previous slide, it's the same thing. You can see that there is proton on either side, proton donor, proton acceptor. They define as not proton, proton acceptor. And they prove that using NH3. If you look at the chemical formula for ammonia, it doesn't have weight, yet it is a base. That is the difference between Bronsted-Lowry definition of an acid. Proton acceptor because of, Lewis structure. This has lone pair of electrons, which a proton will come and sit on top if you accept a proton. So forget about, details of, we'll get into the molecular geometry in chapter 8, but the point here is the definition of an acid and a base according to Arrhenius, according to Lowry-Bronsted, and then in Chem 2, you will cover the Lewis acid and Lewis base, where he defined an acid using electron donor, electron pair donor, electron pair acceptor. So coming back to that, we have defined an acid. You can give an example of that. And there is also, apart from knowing the definition, we will see, or you will be required to memorize and classify an acid as a strong acid, strong base. We'll see that, but for now, acids are substances that ionize. The word ionize here is to split. We were ionizing ion in the previous section, so it will split to produce ion in H2O. Hydrochloric acid in H2O, this is water molecule. The water molecule will absorb the hydrogen, the chloride give us the formula for hydronium ion. You may see sometimes on that the hydrogen, just for your general information, if we dissolve in H2O, right, this hydrogen ion will not stay by itself, but it will, the water molecule assume this molecular geometry with partial positive, partial positive, partial negative because of electronegativity. Will come to that. The hydrogen, which is division of an electron, it needs a negative to neutralize or to pair up with this. Remember, classical physics, positive and positive, they don't like each other. Positive, negative, they do attract. So we end up with hydronium ion. So you may see this down the line that anything that produces hydronium ion, what is the hydronium ion? The more hydronium ion, the more it's acidic. So bases on the other side, they produce hydroxide ion when dissolved in H2O. So here we are still referring to Arrhenius definition of PACE, whereas Bronsted-Lowry is basically proton acceptor. It's good to distinguish between the two because chapter 16 in Chem 2, you will come back again to acid and bases in details. So what is happening here is in H2O, when ammonia is dissolved, according to Bronsted-Lowry, when ammonia, which is considered as a base, is dissolved in H2O, it will abstract or remove the hydrogen from the water molecule. In the process, hydroxide is generated. It is generated from H2O. That is why the solution will be basic. This is a gas. If we bubble ammonia gas in H2O, we'll end up with a basic solution. So with that definition, please write your own notes. Understand that there are two versions at this point: definition of an acid, definition of a base, according to three scientists. Two of them work together, Bronsted and Lowry. There are two of them. That's why it is even Bronsted-Lowry. Two people came up with their own version of definition of an acid and a base. We have now to be able to differentiate between strong acid and strong bases. When we say strong acid, they ionizes or dissociate completely. What that means is a strong acid, all right? Strong acid, we have, let me just use the acid first of all, most acids as strong acid dissociate 100%. That means it ionizes. Sometimes you may see this 100%. What this means is, let's say an example is HCl. If we have 100 molecules of HCl, this is a strong acid, it will produce 100 H plus and 100 chloride ion. I'm splitting that 100%. It will split here. It will dissociate right here. I had 100 of them. So I'll have 100. That is what is meant by strong acid. Strong acid completely dissociate. Weak acid partially dissociate. Sometimes this is weak acid. About 5% dissociation. That means it will ionize only 5%. An example of weak acid is hydrofluoric acid. It's a weak acid. Remember, the benchmark most others use is 5% ionization or dissociation. So if I have 100% of a weak acid such as hydrofluoric acid, it will mean I will have 95% hydrofluoric acid. It will not dissociate. It will remain 95 as molecule, and then 5 hydrogen ion, and then 5, just to give you some analogy here on how to look at the 5% dissociation, 5% dissociation. If you look at it, it does not ionize completely. That's the difference between strong acid and strong bases. Now, you are expected to remember, what constitutes strong acid. Hydrochloric acid, hydrochloric acid is common acid you will encounter, you will work with. Hydrobromic acid, iodic, chloric acid, perchloric, all these, nitric acid, and sulfuric acid. What means is fast proton being removed, because we have two protons here, which not all protons will be removed at the same time. One is removed fast, it will ionize, it will go away, followed by the second hydrogen, which is difficult to remove in that case. So here, please note their names. If you look at his, so that in the future, whenever you are given, you will know. Common weak acid, you will see they are weak, they do not dissociate completely. These includes weak acids, include hydrofluoric acid. Let me give you an example. Weak acid include HF. This is hydrofluoric. All right. Fluoric, the most misspelled element on the periodic table is fluorine. So you have to know how to write fluoric, hydrofluoric. Common acid you will see is CH3COOH. Let me ask you this. What is the name of this acid? Somebody use the chat window. I know some of you may Google and give it to me. What is the name of that acid on my whiteboard?
Acetic acid.
Yeah, acetic acid. It's one of the, yeah, thank you. It is one of the components of vinegar that gives you the tinging taste on vinegar. It's acetic acid. It is one of the common weak acid you will encounter. It will feature prominently in chem to acetic acid. So yeah, Andrea, what was the Bronsted-Lowry acid for? It is Bronsted. Yes, thank you. That is the spelling. Yeah, you get that. Bronsted-Lowry. Yeah, Bronsted acid. That is correct. The definition of Lowry-Bronsted is proton acceptor, proton donor. Simple as that. So.
Professor Lange, with sulfuric acid with the first proton thing, I just want to make sure that I understand it. So whenever the sulfuric acid dissociates,
yes,
would that be that you have one hydrogen and then you still have an HSO4, or is it going to be that you have two hydrogens that completely separate from that?
Yeah, so if we have sulfuric acid such as this, right, and it's aqueous, what this means, the first hydrogen will go away and will remain with HSO4 with one negative. There's an extra. We are removing hydrogen ion, which is the proton, which means whatever electron which was neutralizing the positive in the proton will be displayed by the overall charge on the hydrogen sulfate ion. So what it means by, let me just go back here. All right, here, sulfuric fast proton being removed. That means we have removed, and then now we go back and remove the second hydrogen, and it's very difficult to do that. What this statement means is we may have 98% of the fast hydrogen, and then we go back again, that is remaining. So fast proton, we basically talk about the fast proton in the acid. So no one will ever ask about the second one. So basically we refer to the fast proton wherever we are dealing with sulfuric acid. Hope.
Okay, so it's a strong acid because you can remove the second hydrogen, but technically like in like a first reaction, you would only just remove the first one.
Yeah, you can remove the first one. And if you use that, you see the percent I'm giving you, like the first hydrogen, you lose a lot of the first hydrogen. That very insignificant will remain for the second hydrogen to remove.
I see.
Yes.
Okay, great, thank you.
All right. So that is what it is. And, just mentioning how the protons in sulfuric acid hormone. So I was bringing to your attention, the weak acids, strong acid or strong electrolytes, weak electrolytes, and generally here, remember here we are focusing on the acid and bases. So no ionic compound, it's only narrowing it down to acid and bases. And what constitute the strong electrolytes here are acids. Yes, we know all ionic compounds, electrolytes, weak electrolytes, weak bases, we're gonna talk about that. Most common, I gave you here common what? Acid, right? Common base is, just for your own information, this is a common weak base. This is a weak base, using that so that you know what constitute that weak base. In Chem 2, whatever we do, sometimes in some of the labs we do in Chem 2, they recall, or it will require recalling what happened, or when we say weak electrolyte, what do you understand? They just present to you that this is a weak electrolyte. You have to know the chemistry, that they do not ionize completely to give you the ions. So in neutralization reaction now, having gone through, the definition of an acid, definition of a base, when an acid and a base react, that type of reaction is classified as acid-base neutralization. It's one of the six reaction you will encounter in Chem 1. You should be able to that, so that when we say neutralization reaction, what should come to your mind is hydrogen ion reacting or combining with hydroxide ion to form water molecule. In neutralization reaction, I will use this as a benchmark to classify that as neutralization reaction, because an acid and a base react, and of course an acid will produce hydrogen ion, a base will produce hydroxide ion, and these two will combine to form what? To form water molecule. Where we are going with this now is we will tailor, we will tag to the concept of net ionic equation. And all net ionic equation for acid-base neutralization will produce water molecule. It's not precipitation. Remember in the previous, when we talked about the molecular equation, the complete ionic equation, and the net ionic equation, we always ended up with a solid product, right? Now, in acid-base neutralization, always we end up with, except the one that we will see some which produce gas, which is different from here, but most acid-base neutralization here will produce an ionic compound, which is salt and H2. And this salt will, of course, the ions will form the spectator ions. So if you look at this, why are we going back again to molecular equation, complete ionic equation, and net ionic? Yet we had covered previously. Previously was for precipitation reaction. It is coming back again that we are looking at in terms of neutralization reaction. If I look at this right here, look at my PowerPoint slide. If you look at the PowerPoint slide here, there is H2O, and on my whiteboard box H2O as a reference. In the previous section, we only use solid. So if I am asked the spectator ions, this is molecular. If I'm to write a complete, I will split this. I'll split this where hydroxides. I will not split this. Remember what I say, do not split liquid, do not split gas, do not split solid. So it's the same thing we did before, except that you'll end up, so this is molecular equation between an acid and a base. What you have here is equation 2 complete ionic equation. Look at the ions from the first reagent, which is the acid. We split here, we have the hydrogen ion, and it is aqueous. Chloride ion, it is aqueous. Second reagent, the base. Sodium ion is coming from the base. Hydroxide ion is coming. So if you split this, leave alone liquid, remember the note I gave you, we leave this one alone when writing the complete ionic equation. At this point, you can see which one is the spectator ions. They all look alike the same on both sides, that when you cancel out, you end up with the same, you end up with the net ionic equation. So this is molecular equation for acid-base neutralization. This is complete ionic equation for acid-base neutralization. And this is the net ionic equation for acid-base neutralization. There's some acid-base neutralization which produce gas, and we're not gonna cancel out the gases. Remember what I say? It's not gonna be canceled out. And this is now where you have to distinguish between acid-base neutralization, which gives you H2O as the final product in the net ionic equation, and those acid-base neutralization, which gives you gas. And there are two gases here, hydrogen sulfide and carbon dioxide. Read in the text if this in the PowerPoint slide doesn't make sense to you. Some metathesis, which is acid-base neutralization, double replacement, do not give expected, but they give what? They produce carbon dioxide, which is a gas, and H2O, which is what? Which is a liquid, which means we are not going to cancel out. Let me explain how you're going to, how this might help you in predicting when you do that. And I see in Chem 1 lab, when in pre-lab or post-lab, you do the double replacement reaction and you think that you have the equation. No. Let's see if I do have calcium chloride let's use this. Let's say it's coming from the first reaction here. Carbonate and hydrochloric acid. This is HCl. Plus like that. This will combine with that. This will combine with that. So that if you look on the product side, we have calcium chloride, yes. And of course, you use the solubility table to predict whether it is aqueous. This is aqueous. Plus, what is, you may expect this to form, right? This is carbonic acid. I'm giving you what is going on here. Why don't that just do double replacement if this metathesis reaction? Why can we just leave the way I do have in my PowerPoint slide and use the solubility chart? It turns out that this one carbonic acid is unstable and it will dissociate. It will dissociate to form H2O, which is liquid, plus C carbon dioxide gas. So that's what's happening. You need to understand why we end up with this versus not this. This is unstable. It will dissociate immediately as it's formed. It did dissociate to form what? To form carbon dioxide and CO2. That is where this is coming from. That is where this gas is coming from, and the liquid H2O is from the carbonic acid, and cars forming reaction is just some of the reaction you will see. Hydrogen sulfide is an example. Rarely will you see this, but the most important is the one I just went through. And in real application here, let's understand what is going on or what goes on when you take antacid. At some point, some of us, we may have taken this. If you haven't, you're lucky, all right? Hope you will not have acid reflux and stuff like that. The reason why, or a real application for this is when antacid, which some of these antacid, they inhibit. That means they stop the production of the acid. Some of these work by neutralizing the acid. If you look at this is what? This is an acid, and if you have an acid, all of them, they do have their acid neutralizing, their bases. They do have what? They do have hydroxide. In the equation, in the previous slide, we were given carbon dioxide. I mean calcium carbonate, and if there is an acid from the carbonic acid, this will neutralize the acid in the stomach. There is a note in the text, please read on that more on the application of metathesis reaction in gas-forming reaction. Gas-forming reaction has real application in the acid. I'll not ask you, give an essay or how it works, but the real application here is those gas-forming reaction, neutralization, metathesis. Among the six types of reaction you should know is oxidation reaction, oxidation reduction reaction.
Can I actually ask one quick question before we move on?
Yes.
So it was, I actually have two, but they're very quick. So one of them for salts,
Yes.
with the neutralization, anytime that like you just do that double replacement, is the salt just basically going to be that ionic compound that just comes out of it, and that's kind of what that's saying?
Yes, it's gonna be aqueous. It's gonna be aqueous. It's not gonna be ion. Yes.
Okay. And then for the antacids, were you just saying that like you're not gonna like have us like memorize that chart, but just kind of like sort of like understand how it would work?
Yeah, how it works, like by neutralizing the excess acid in the stomach.
Okay, great, thank you.
Mm-hmm. So let's shift gears to a special type of reaction we call redox. This is abbreviated as redox, like that, for two types of reaction. There's reduction reaction and there is oxidation reaction. It cannot take place, oxidation cannot take place by itself. They do take place at the same time. And oxidation like that, or in short, reduction oxidation reaction is a reaction where involve transfer of electrons. And remember, in subatomic particles, here involve what? It's a type of reaction which involves transfer of electron. It can be more than that. It involves redox reaction. Here you see here are electrons which involve transfer of electron. Electron is moving from one species to another species. For example, here and chlorine, those are neutral atoms, for example. But if an electron is transferred from sodium to chlorine, we end up with sodium ion and we end up with chloride ion. Positive and negative to attract, which means Na positive and Cl negative, they attract each other, so they just stay like that, and this is the formation of sodium chloride, positive and negative. It involves transfer of electrons, So two types of electrons, two types of reaction. Oxidation here is loss of electron. Oxidation is loss of what? Loss of electrons. Whereas reduction is gain of what? Gain of electron. It's redox. It can be an electron or electrons. So I'm putting in parentheses. It could be. Oh, I forget to put my charger on. Hold on. We're in business now. Thank you. So reduction is gain of electron. If you look at the flow of electron here, chlorine is gaining, sodium is losing. There is loss of electron, there is gain of electron happening at the same time, hence the word redox for reduction, red for reduction, ox for oxidation. So two types of reaction taking place, loss of electron, gain of electron. To really nail down that, we have what we call oil rig. You know, oil rig, when they mine or when they drill oil off the earth, you know, oil rig, they have a rig. So here is to help you out in divining that oxidation is loss of electrons, That's how you divine oxidation, oil, and then here reduction is gain of electron. This is how you memorize and commit to your memory the two types of reaction, oxidation reaction. Across the nation, even in Harvard, you know, students do have a problem in oxidation reduction reaction because there are 6 terms you need to commit to your memory. There are 6 terms. So far, we have covered 2 terms. Remember, there are 6 terms. Or 2 definitions you should know. We have defined oxidation, we have defined reduction. We are remaining with 4, which I'm going to highlight. All right. So that is what you need to know, that redox is a special type of reaction. And it involves transfer of electron. The 2 terms which I will add to the 2 we have already defined is what is oxidized and what is reduced. Look at the PowerPoint slide. There is a term here, reduced, and what is oxidized. If oxidation reduction reaction involve transfer of electron, to understand what is being reduced and what is being oxidized, I always use, you know, I don't know if this will make sense to you, using the traveling agent. You know, when you say traveling agent, somebody who doesn't know traveling agent might think traveling agent is travel a lot. No, traveling agent make people to travel. So here in this, if chlorine is making, if you look at the diagram on the whiteboard, chlorine is making sodium to lose electron. Chlorine is on the other side. You need to know where you position yourself. So assuming we are chlorine or you are chlorine wherever you are, and we are making sodium to lose electron, we say that this is oxidizing agent. It is oxidizing what? It is making sodium to lose electron. If oxidation is loss of electron, oxidizing agent is making the other species to lose electron. It is to receive, it's on the receiving end. Whereas what is oxidized is reducing agent. If reduction is addition of electron or gain of electron, the species which is adding electron to something else is the reducing agent. So apart from reduction, oxidation, which is easy to remember, to commit to your memory, you need to know what or you need to know the reducing or identify rather, you should be able to identify the reducing agent. You need to be able to identify an oxidizing agent. I've not covered that, but I'm in the process of defining oxidizing agent, reducing agent. We're gonna come back to that. And what is reducing agent is oxidized. Reducing agent here is oxidized. And oxidizing agent here is reduced. Oxidizing agent is reduced. You add electron, it's made. And that is why when you look on the PowerPoint slide here, look at the PowerPoint slide. Why is calcium oxidized? It is made to lose electron. It is a reducing agent. Oxygen in this reaction here is an oxidizing agent. It is making calcium to lose electrons. It's oxidizing agent. It's making lose electron. How will you know that what is which? We cannot. I'll not recommend that you memorize that this is what it is. There is another concept which will be handy in nailing down what I just went through. I've defined that, right? We have no problem with. We have no problem with defining oxidation. We have no problem defining reduction reaction. Here, gain of electron. I gave you the oil. Remember this? No. Remember this oil? That's how you define those two terms. Oil. Oxidation is loss of. That's how I know that.
So I know that you used NaCl, sodium chloride, for your example, but I thought that oxidation always had to have oxygen in the reaction.
Let me see. Let me see here.
Yes.
You get what?
I'm sorry.
What is the question here?
Because I wasn't seeing oxygen, and I just wanted to make sure. Like I thought that oxidation always had to have oxygen somewhere in the equation. I know that.
Oh yeah, that is. Yeah, I like. Yeah, that is. Initially, in the 17th centuries, when they defined oxidation, they meant or they were using addition of oxygen, but nowadays they remodify the definition of these terms, basing on the electrons. But initially, when this concept was introduced, or whoever came up with this concept, they were using the oxygen. So it does not necessarily involve oxygen. For example, here, you may see in the PowerPoint slide, oxygen is involved, and you may think that always oxygen has to be involved in oxidation reaction. No, it involves transfer of electron. That is a one-size-fits-all definition of oxidation reduction has to do with electrons. But in the 17th centuries, when the first person came up, it involved, addition of oxygen, removal of oxygen, and stuff like that. Does that make sense?
Okay, so if like kind of going back to our earlier chapters, if you have like just like a combination reaction, like with NaCl, it can also be oxidation because of that transfer of
Yes, yes.
Okay, great. All right, thank you.
So we didn't have to talk about oxidation and stuff like that because of, you know, like this one, when we go back to balancing the equation in chapter 3, there was some, of course, oxidation reaction taking place. So looking at this equation here, it will not help you in identifying here, nailing down here. My concern is how will you identify the reduction, oxidizing agent, reducing agent, what is being oxidized, what is being reduced. This will call for keeping track of what we call oxidation numbers. Oxidation numbers will help us understand or identify the reducing agent, oxidizing agent, what is being oxidized, what is being reduced. If you can nail down how to keep track of where the electrons are going, where the electrons came in, how the numbers are changing, you can identify the reducing agent, oxidizing agent. What are oxidizing numbers, first of all? Oxidizing numbers are just the numbers given or assigned to an element in a compound. And we can use the periodic table, but in some cases, we do not use the periodic table to really assign the oxidation number. And I'm going to show you where and when the periodic table for main group element will be used and why sometimes we do not use the periodic table, even though you may be looking at the same element. Oxidation number to each element in a neutral compound. What do we mean by neutral compound? Or charged entity? This could be polyatomic ion. For example, charged entities here, it could be nitric acid like that, or this is a charged entity with an overall charge of -2 like that. This is a neutral compound. The first one is a neutral compound. Charged entities, polyatomic ion. We should be able to identify that. It is a bookkeeping. It has nothing to do with what I just said. You need to summarize on 4x6 index card these rules. Rule number 1 is atoms in their elemental state have an oxidation number of 0. If it is just by itself. Elemental state. What do we mean by elemental state? If I have sodium, for example, this is an element in its state, the oxidation state is 0. It is not positive 1, you may think. It is in group 1. If it is ion by itself, how will I know that, if it is solid ion, solid sodium, they are in elemental state and the oxidation number ON have a 0, as opposed to when they are in monoatomic ion. Ions are charged particles. These are monoatomic ions. So here, oxidation ON, let me just write here, ON equals to 0, ON equals to 0. Oxidation number are 0 for elemental state, when they are in elemental state. But for monoatomic, that means it is 1. Ion, that means it is charged. Sodium ion, this has +1. Sulfide ion, negative, this has -2, sorry about that. This has -2. Phosphide, This has -3. The oxidation state for one atom is the same as its charge. So if it is +3, ion 3 like that, this is +3. So you need to know if it is monoatomic or if it is in elemental state. Now, rule number 3, non-metals usually have a negative oxidation number. Non-metals, you know where they are. They are on the right-hand side of the periodic table, and most of them, unless you are given here in rule number 3, they have oxidation state of -2, hydrogen. If it bonds with non-metals, they are +1, fluorine, and so forth. So basically, if I'm using periodic table for non-metals, generally the ionic charge for that corresponds to their charges. Now, for polyatomic ions, such as the sulfate, for example, here, sulfate ion with an overall charge of negative, how do you assign? Even before we get there, hold on. Even before we get to polyatomic ion, let's go to, sorry about that. Let's go to sulfur trioxide. It is a neutral compound. I wanted to say neutral. Let's underline the word neutral here. And I'm going to highlight how you assign oxidation state to each element in a neutral compound. If you are given, before we look at polyatomic, if you are given a neutral compound, the first priority goes to the more electronegative, the one, maybe I'm using for the first time a terminology here, more electronegative. The one on the left side, on the right side, when you write the chemical formula, take first priority in using the periodic table to assign the oxidation state. So oxygen is in group 6, and it will have an oxidation state of -2. It will take first priority. And then now, even though oxygen and sulfur, they are in the same group, you cannot use the same approach and say, all right, let me just make it -2. Also, you have to do the math. Yeah, anything on chlorine, take first priority. Thank you. Fluorine is the most electronegative element of the periodic table. So that is how I'll take first priority in using the periodic table to assign the oxidation state and say it is in group 6, it's in group 5, it's in group 7, it got -1, it got -2, or -3. And then you do the math now for the less electronegative element and equate to 0. You see here? The sum. So I will say, let X, you say, let X P oxidation number for sulfur. And then you do the math and say X plus -2 times 3, because we have 3 oxygens, all right, equals to 0. You equate to 0 for a neutral compound, which means X, all right, X equals to, or -6 equals to 0, which means X equals to what? Equals to +6. It's not always going to be +6. I've seen examples where oxygen, sulfur is +4, sulfur is +2. It varies from compound to compound. You need to do the math. Somebody has a question?
Yeah.
Yeah.
So this is for neutral compounds,
For
correct?
neutral compound, thank you. I'm going to show you for polyatomic ion. Let me do one example on neutral compound where you have to use 2X. Suppose we have nitrogen, dinitrogen pentoxide, for example, it's a neutral compound, right? So as we said, the most electronegative element close to fluorine, as Claire pointed out, yes, that's true. And use that. Take first priority and say oxygen is -2. And then you let what? Let X be oxidation number for nitrogen. In this case, the calculation here is you have 2X because of 2 nitrogens plus I have 5 oxygens times -2 equals to 0 because it's a neutral compound. It's a neutral compound. So 2X minus 10, this is third grade maths, equals to 0, which means 2X equals to +10. If I divide both sides by 2, divide both sides by 2, which means X equals to what? +5. So I'll say nitrogen is +5. Each nitrogen is +5. You got to do the math if you have a subscript S2. So always the most electronegative take first priority, you got to know how you assign that. That is for a neutral compound. It's a different ball game when you have polyatomic ion. Polyatomic ion, you have to equate to the overall charge. Example is, let's say we have a sulfate ion with an overall charge of -2. With an overall charge of -2. This is a polyatomic ion with an overall charge. The sum of the oxidation numbers in polyatomic ion is the charge on the ion. So we will say oxygen take first priority, which is -2. The most electronegative, just the way we did for the neutral compounds. Oxygen take first priority. For sulfur, you say let X P oxidation state for sulfur. You do the math now and say, watch this. X for sulfur plus we have 4 oxygen times -2 for each oxygen equals to -2. The -2 has nothing to do with the -2 here. It is from the overall charge, the ionic charge for polyatomic. The ionic charge for polyatomic, which means X minus 8 equals to -2, which means X equals to -2 plus 8, which is +6. So this is the oxidation state for sulfur in the sulfate ion. Question is, I see you see in the post-lab or pre-lab, if you are taking the course right now, there is, all right, you'll do a post-lab or pre-lab where say assign oxidation state to each element, or what is the oxidation state for each element in the following. Each element, when they say each element, that you have to look at each element in the compound. Do not just give the ionic charge and think that that is the oxidation state. This is not the oxidation state for the sulfate ion. We are looking for each element. So remember to equate the overall charge, and then you do the summation. In both cases, you have to do the summation. Let's see. Suppose we have a neutral compound with 3 elements, such as nitric acid. That is what you will do. How you go about with this? In most cases, the central element is the last one you will be looking at. The first and the last, you use the periodic table to assign, the oxidation state. And in this case, Oxygen is -2. All right, hydrogen. So this is +1. This is -2. Let XP oxidation state for nitrogen. So if we say +1 for oxygen, for hydrogen, sorry, plus X for nitrogen, plus -2 for each oxygen times 3 like that, equals to 0. This is a neutral compound. This is for a neutral compound. X plus 1 minus 6 equals to 0. X minus 5 equals to 0. X equals to +5. So that's how you go about when you have, more than one element. Most electronegative take fast priority using the periodic table to predict the ionic charge. Ionic charge is basically the oxidation number here. Ionic charge is basically the oxidation number we are referring here. So nitrogen is +5 if we are to assign each element in that compound. So here is +5, +5. I don't want to copy on the single displacement replacement reaction, single displacement reaction. We will start from here on Thursday. Please continue working on chapter 4. Start reading chapter 5. Form study group. All right, we are doing a good job. We also, if you came in, if you join us in the middle of the lecture, the average score for the first exam was 89, which is good. All right, please continue using the SI support and form your own study group. You can use the Zoom, share your screen, whatever. We don't have to, be in the same room to really form a study group. Other than that, thank you. If there is no question, we will meet again on Thursday, same time. Thank you for tuning in. The class is dismissed. I'm gonna stop sharing my screen if there is no more question. See you on Thursday. The class is dismissed. Thank you.